Welcome back. This is an Aleks training video on interconverting wavelength, frequency, and photon energy. So a photon of light has a lot of power. It can make a plant turn carbon dioxide and water into sugar. It can remove electrons off of a metal. It can make electricity move inside a solar panel. So it has energy. It has a punch to it, and so in chemistry, a lot of times, volatile chemicals and chemicals that are very prone to break down in the presence of light will be stored in dark bottles, like dark brown bottles. Hydrogen peroxide is always stored in a brown bottle because light can break that down into hydrogen gas and water, and then that hydrogen gas builds up and explodes the bottle. So even though plastic is a little more safe than glass, it's still in a brown plastic bottle so that it doesn't explode. In any case, light can do this, and so their question here is they give you a certain amount of energy that a photon of light, now a mole of energy, for a mole of chlorine-chlorine bonds, so Cl2 molecules, for every mole, it takes 242 kilojoules of energy to break all those bonds. So if you know that much energy, calculate the wavelength of light to which a chlorine-chlorine single bond could be broken by absorbing a single photon. Okay, so one photon of energy, of light energy, and it will break one single bond. I call this a hard question. I'll give you a little bit of information, though, that you don't know. There's a formula derived by a scientist named Planck. It looks like Planck to me. And they, at the early part of the 20th century, they were studying light, and Einstein did this and a lot of his work, and realized that light is quantized into a photon of energy, and that energy can be, that the amount of energy can be quantized into a little bucket or a little particle of light, and then the number that makes that work is called Planck's constant. And Planck's constant is, I'll write it down. This is called Planck's constant. And so by using it, you can convert energy into frequency of light. And then we can take frequency and put it in the speed of light formula that you already know and find out what the wavelength of that light is. So Planck's constant is equal to 6.62607 times 10 to the minus 34 joules times seconds. Okay, so energy over time. And it's the number that makes this relationship work, that you can relate energy of one photon to the frequency of light of that photon. So if you know the frequency of light, you can know how much light one photon of energy will give you, and this number makes that happen. That's what the Planck's constant is. Okay, so by knowing this, you're going to see that this is the energy. It takes 242 kilojoules for every mole to break all the bonds. So we're only wanting the energy of one single bond. So we want one molecule, not a mole of molecules. So we want to first take this down to be how much energy is it going to take for one molecule. So we know that if there's 242 kilojoules in 1 mole of molecules, okay, all right, and in 1 mole of molecules, there's 6.02214 times 10 to the 23rd molecules. Then, when I divide that out, so 242 kilojoules, right? So 242 divided by 6.02214 times 10 to the 23rd, is going to give you 4.0185 dot 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 times 10 to the negative 22nd power, and this is kilojoules. All right, now I want to cancel. Okay, so because I'm going to solve for frequency, so I'm going to divide by the h, divide by Planck's constant, and Planck's constant is in joules. So I want this to be in joules too. So let's just go ahead and put it in joules. In 1 kilojoule, there's 1,000 joules. Kilojoules will cancel. Okay, that means it's going to be 4.0185 dot 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 times 10 to the negative 19 joules. All right. So this is E. That's energy. All right. So I have energy equals Planck's constant times frequency. I want to solve for frequency. So I have E over H equals frequency. My energy is 4.0185 times 10 to the negative 19 joules. Planck's constant is 6.62607 times 10 to the negative 34 joules times seconds. Joules will cancel. My answer is going to be in hertz, which is something with a unitless divided by seconds, cycles per second. So I have divided by 6.62607 times 10 to the negative 34. Okay. It gives me 6.064688 whatever times 10 to the 14 cycles per second. All right, so this is V. This is new. Well, you know from previous work that the speed of light is going to be equal to your wavelength times your frequency. And speed of light is a constant, so you can look that up, and you've just found your frequency. So you're going to divide your frequency into the speed of light, and it'll give you your wavelength. So looking it up, now I remember it as 3 times 10 to the 8. I think that Aleks is more picky and wants it more specific. So Aleks has a data bank that you just push the data button and it'll give you all this information. 299792458 meters per second divided by 6.064688 times 10 to the 14 seconds to the minus 1, so this will cancel with this, leaving you meters. Okay, I get 4.9432457 whatever times 10 to the minus 7 meters. All right, so I'm not going to have something this tiny in meters. You don't have something with 7 zeros or 8 zeros in front. So what you're going to do is you're going to multiply by something so you can put it in units so that it's a number. It's like a 10 or 100 or 500 or something like that. Not 0.5 or 0.0005. You need units that make sense. So the units that I know are 10 to the negative 3 is milli, but that's not enough. That's still going to be a decimal. 10 to the negative 6 is micro, but that's still going to be 0.494, which is still too small. The next unit is to the 9, 1 times 10 to the 9, which is nanometers, and that's probably the better one. So if I say that in 1 meter there's 1 billion nanometers, and meters change, that means it's going to be 494 nanometers will be your answer. So that makes sense because light is from 400 nanometers to about 700 nanometers. So anytime you're talking about light, you're going to be in nanometers. Nano is a unit small enough to be inside a human cell. So nano, there's a whole technology now, nanotechnology. It's a billionth of a meter is how big it is. All right, hard, I think, but you can probably do it if you work.